Hello, and welcome to the Magnetic Forces and Fields unit of PHYS 1201. And in this first lecture, we're going to look at what produces magnetic fields and a little bit at what magnetic fields do. I'm going to introduce several very basic aspects of magnetism. You should have all seen this before, but I find many students come into this with some really serious misconceptions. So everything we call a magnet has two poles. And if you hang a magnet so that it's free to rotate, it'll align with one of those poles pointing north. So we label the poles north and south, or more precisely, we'll call them north-seeking and south-seeking. And a compass needle is a magnet. Now, what's going on is that it's interacting with the Earth, which is also a magnet. And you can observe that opposite poles attract and like poles repel. That property allows you to identify which pole is which on a magnet if you don't know which is which. So for example, this rare earth magnet is unlabeled. The red end of the compass needle is the north-seeking end. The black end is the south-seeking. So now since we see one face attracts the red end and the other face attracts the black end, then the face on the left must be the south-seeking end, and this one on the right, which attracts the south-seeking end of the compass, must be the north-seeking end of this rare earth magnet. So here I've wrapped a rare earth magnet in paper and labeled its north and south poles, and I've got a stack of rare earth magnets that I've put on rails so that they are held to slide back and forth and not rotate. And you see the north-seeking pole will repel one side, the south-seeking pole will repel the other side. But if I flip it around, attract. Well, all of that you've probably seen, but now we come to the first misconception that I often see students have. Either pole of a magnet will attract ferromagnetic metals. Not all metals, only ferromagnetic ones. Now, the most common ferromagnetic metals are iron, nickel, and cobalt. So I see two misconceptions. First of all, some students think that a magnet will attract any metal. But the other thing I often see is that students sometimes think that the North Pole will attract and the South Pole will repel a metal. But that's not true. Either North or South will attract a ferromagnetic metal. Now, something you may not have seen is that if you take a magnet and cut it in half, you will not get one magnet which is north-seeking and one magnet which is south-seeking. You'll get two magnets, and each of them will have a north pole and a south pole. I'd like to show you cutting a magnet in half. I don't have any cheap disposable magnets, but I've got lots of nails. And if you've got nails and magnets, you can make as many more magnets as you want. So I've magnetized this nail there. You see that's clearly the south-seeking end because it attracts the north-seeking end of the compass, and that end is clearly the north-seeking end. So now I'll cut this nail in half. And now here's half of the nail, and you see that one end attracts the south-seeking end of the compass, and the other end attracts the north-seeking end. So I've cut the nail in half, and half of the nail is a complete magnet with two poles. So magnetism is different from electricity. The other thing to note is that charged objects will attract a magnet, but they'll attract either end of a magnet, the north end or the south end. That's because all that is polarization. A charged object will polarize a magnet just like it'll polarize anything else. So that's not a magnetic interaction, that's an electrical interaction. So the north pole of a magnet is not a positive charge. The south pole is not a negative charge. Magnetism is not charge. Magnetic forces are not electrical forces. And the other big difference is that positive charges and negative charges can exist in isolation. You can have a charged object that is either positive or negative, but every magnet has both a north pole and a south pole. Isolated north and south poles don't exist. Well, we think they don't. We need a definition for the direction of our magnetic field. For electrical fields, we worked in terms of forces on electrical charges, which we called probe charges. For now, and this is not the formal definition, but the formal definition is very confusing. So we're going to work with a much less confusing definition, and it's in terms of a compass, because that gives you an experiment you can carry out. So, as usual, we define the field as a property of a point in space. And we will put the compass at the location of space we're interested in. And the way that its north-seeking pole points is going to be defined as the direction of the magnetic field. So if we put a compass right here, then we're going to find that its north-seeking pole is repelled from the north-seeking pole of this magnet, and its south-seeking pole is attracted to it, and so the compass would point this way. And so that is the direction of the magnetic field at this point. And similarly, if we put it here, it would point roughly like this, and so on. If you put it near the other end, its north-seeking pole is attracted to the south pole of this magnet, and its north-seeking pole is repelled, and its south-seeking pole is repelled, so it would point that way. And if you continue, you would find that it does something like this. Now, if you were to disturb the compass anywhere in here close to the magnet, you would find that it quickly snaps back. But if you were to try that farther out, you would find that it rotates more slowly. That's our first hint that the magnetic field is weaker out at larger distances. But we will in the end have to define strength of a magnetic field in other ways. What I've just drawn are magnetic field vectors. Just as with electrical fields, instead of drawing field vectors, we can also draw field lines. So again, the field has to be tangent to the field line at every point. And where field lines are close together, that tells us that the field at that location is strong. And where they're far apart, the field there is weak. Before moving on to the main thing that we're going to talk about, which is magnetic fields produced by electrical currents, I do want to say one or two things about the Earth's magnetic field. So of course the reason a compass works is that the Earth itself can be thought of as a giant magnet. It has a magnetic field that it produces. And what produces it is electrical currents in the Earth's core. And while we understand the basic mechanism of this, the details are actually surprisingly poorly understood. In any case, if you think about what that means, that the north-seeking pole of a compass points towards the north pole of the Earth, but opposite poles attract. And so the magnetic pole near the north geographical pole must be a south-seeking magnetic pole. A little confusing at first, perhaps, but it makes sense if you think about it. But that's confusing enough that if you look around, you'll often find wrong diagrams. I found this wrong diagram on a course website at a university that will remain nameless. Anyway, the magnetic poles are not quite aligned with the geographical poles, and in fact they wander about a little bit. So here's a map showing the location of the north magnetic pole at various years. With electric fields, all the electric fields we've really talked about are three-dimensional. But you can usually draw two-dimensional pictures of them and basically capture the idea of what the field looks like. But for various reasons, magnetic fields are relentlessly three-dimensional, and so we're not always going to be able to avoid drawing situations where there are vectors coming out of the page or into the page, and so we need to know how to draw them. So here's a vector in the plane of the page, but when a vector is coming out of the page, we draw it this way. And you should imagine this as the point of the arrow coming out of the page at you. And that's how you remember that that's the symbol for the vector coming out of the page. Sometimes we just draw a dot and leave out the circle around it, but I'll tend to draw a circle with a dot in the middle. When the vector is going into the page, we draw it this way. And that might seem like a funny symbol for you, but the way to think about it is, well, this is an arrow. What's at the back end of an arrow? Well, feathers, of course. So here you're seeing the feathers. So far, I've mostly been talking about permanent magnets, things like rare earth magnets and compasses that we're fairly familiar with. But those permanent magnets actually turn out to be extremely complicated. What's easier to understand is the magnetic fields that are produced by currents in wires. So here is a wire, and the current in this wire is running upward, like so. And if you look, you can see that the magnetic field is that way in front of it, and this way over on this side, and this way over on this side. We say that the magnetic field due to a wire follows a right-hand rule. And here's what's meant by that. If you wrap your fingers of your right hand around the wire so that your thumb points in the direction of the current, then the way your fingers wrap around is in the direction that the magnetic field points, right? Over here this way, in front this way, over here this way, and behind the wire it would point this way. So, getting used to the way we draw this, here I've drawn the current coming out of the page at us, right? The dot with the circle around it. And if you hold up your right hand with your thumb pointing out of the page like that current and curl your fingers, then they're going to curl around in the direction that this magnetic field is pointing. And I'll just point out this B. We label the magnetic field with a B vector. Why not M? Well, M was taken, but there's actually another reason, and it just has to do with that the person who assigned the letters just started at the beginning of the alphabet, and when he got to magnetic fields, he was on B. Now, here it is with field lines instead of field vectors. And now if the current goes into the page, point your thumb into the page and curve your fingers with your right hand, and your fingers will be curved around in the sense that these B field vectors are pointing, or if you prefer, these B field lines. Just to practice our new vector notations, here I've drawn these vectors in and out of the page without the circles around them, but this still means vectors out of the page here and into the page down here below this wire. And so if you picture the circular field that this wire must be producing, if the vectors are coming out of the page here and into the page here, they must be coming down in front of the wire and up behind the wire. So if you hold up your right hand and make your fingers curl so they come out above the wire and stick your thumb out, you're going to conclude that the current in this wire must be running to the right.